So I want to start generally. My work, my PhD study is about protecting industrial control systems and critical infrastructure. So normally, for designing countermeasures against the attacks, we have to, like anything else, have to understand the attack itself. And well, we were studying ICS networks, like understanding how different components of ICS networks are working. So you have information technology domain, you have operation technology, and you have actual physical application. And in this case, like there is always a hacker, not this guy, who actually try to cause damage to the physical process. And so the first step for us was that to understand how somebody can actually get access to such network. And based on that, we were doing a research in 2014 about how somebody can access to the networks which are highly secure or like having some kind of virtualization-based protection systems. And we already published about it. The next step was to understand, OK, the attacker is in, what we want to do. And that was another work, actually. So we were actually studying different utilities, electrical grid, water utilities. So we first started by looking at the basics, so how the process is actually working. So in order to get a better understanding of the process, how the process is working generally, and then going more into the details, looking at specifics in the process, what kind of equipments they are using in different processes, what kind of, for example, PLCs, sensors they are actually using. So we continued more and more on this to understand better the industrial process, different processes. So not just, for example, in this case, water, but also electrical grid, electrical distribution, electrical generation, gas storage networks. So lots of critical infrastructures. And then we actually designed some kind of process exploitation attacks. What is the shortcomings of the process and how somebody can actually exploit it, which I talked actually in S4 US this year about it, partially, not fully. So here's a big picture. So we wanted to see how somebody can exploit a process. But the first step for us was that, obviously, this picture will be much more complicated normally. But first step for us was that, OK, somebody have to get access to the network, right? And next step is that the attacker must actually understand the process. And then, normally, like in a very, very basic form, everybody who's seeing is that, well, you manipulate the PLC framework or manipulate the PLC logic, and then you exploit the process. But it turns out that actually it's not true, because at least in academia, there was researchers that suggesting some host-based intrusion detection for the PLC itself, meaning that you cannot just access to the PLC and do whatever you want. And that actually was another research. So we were working on different kind of protection mechanisms within the PLC itself, at least in academia. So, for example, it's not anymore possible to just upload your own framework or like manipulate the logic without having a logic check somewhere checking the logic itself. Also, even interestingly, they also had some kind of malware detection mechanism. So, for example, hook detection within the PLC itself. So you couldn't just write a malware hook functions within the PLC runtime to do bad things. So that's where actually it's a recap of what we did. And we were looking at actually how PLC controls the I/O in order to understand how we can actually bypass those protection mechanism, host-based protection mechanism within the PLC. So we were looking at how a PLC runtime interact with the physical interfaces it has. And we came to a concept called pin control subsystem, which had two generic rules in it. So you have two things in a pin control subsystem, pin configuration and pin multiplexing. So the SoC vendors for embedded softwares or embedded domain, they actually provide this SoC for different kind of vendors. So they sell it to you, but also they might sell it to a phone manufacturer. So what they do is that they want to provide the SoC pins functionality to different kind of other vendors. So what they do is that they put a functionality that you can switch the functionality of the pins within the SoC. So that's multiplexing, which it's saying by itself. So we also looked at something else, which was pin configuration. So digital I/O interfaces of the devices. They actually are getting configured in a way that there is a generic rule for it, meaning that the a digital I/O pin can be either input or output. And the rule is that if you define a pin as an input, you can never actually use it as an output pin. But if so you can never write to a pin which is input. And similarly for output pin, so you can write to it. And of course, like you can also read to it because there is no limitation on reading from a pin which is output. And there, we were looking at this concept and looking at how operating system of the PLC actually mapping a physical memory of the I/O to a virtual memory. And then, for example, somebody uploaded a program logic to the PLC and asking to do something specific. So here we say, for example, if one pin value is true, then in another pin, every 5 seconds, I want to, for example, turn it on and off, meaning that I want to write values 0 or 1. And that's how it was working. So the PLC was actually writing the configuration of the pins to a virtual memory. And then this value was getting written to the physical memory. And then the PLC logic was starting to read the values from the virtual memory, which was the data was coming actually from the physical memory. And then once the condition, which was if one pin value is true, then another pin every 5 seconds have to get turned on and off, the PLC was starting every 5 seconds writing a value to the pins. And that was the whole concept. But what we did as an attack was, and as an attacker, was that we said, what if somebody here, as an attacker, comes and change the value in a configuration of a pin? We noticed that there is no hardware interrupt to notify the PLC or operating system kernel that, hey, the configuration of the pins are changing. So what happened was that we just changed the configuration in the virtual memory. This value gets written to the physical memory, but without PLC runtime knows about it. And the PLC was thinking everything is fine, still writing a value 0 or 1 to the output pin, while we changed the configuration of the output pin from being output to input. So we changed entirely the configuration of a pin. But remember, you cannot write to a pin which is input, as we say, general rule. So what happened was that the PLC write this value to the virtual memory, and then this value have to get converted to physical memory, get written to the physical memory. But it never happens because a pin is actually in input, so there is a write failure. And what happened was that we could actually bypass all of those host-based intrusion detection protection systems within the PLC without actually doing any kind of, for example, function hooking or like intrusively target those area which protection mechanism we're looking at. So we bypass all of those host-based intrusion detection products. Now we have actually a demo for that, 2 demos, which we can see. So here's one PLC. Actually, we covered the name of it, so we don't want to mention it. So which there is LEDs running on and off every 5 seconds, and then we are actually running our own attack. And what will happen is that we are manipulating in the same way as we said, but the PLC runtime doesn't know about it. So there is no log output or anything about this issue. So now you can see the value blue. When it gets blue, it means that the LED is on. When the value inside the PLC, you see it get dark, it means that the LED is off. So and then we are doing executing our own attack, which takes a little bit time to kick in, but after some seconds it comes, and then we control the I/O. While you see in the software, in the PLC software, is that the PLC software still assumes that the values are changing every 5 seconds. So you can see that the value goes false and true, but it's not anymore the case because actually we are controlling the LED. So this was just one basic example. And we actually first time, so we can see actually, yeah. So we decide when we want to turn on and off the LED, but as you can see in the software, it's still saying value true or false, which is not true because we are actually in control of the hardware. If we go to the next demo, so actually, first time we were executing it in a Raspberry Pi because we didn't have a PLC. So here's an example. It's like a motor which you are controlling. So every time you are pressing the motor button, then motor goes faster. And what we do in this case is that we actually use the same concept because we are targeting the SoC. It's not at all related to a PLC. It actually works in all embedded systems. And what we do is that we are actually taking control of the physical buttons there. So the user tries to press the button, but the button is not anymore working, meaning that we are actually moving the motor so fast, and it's not the user or the control software is not anymore in control of the hardware. So this case was a pin multiplexing, multiplexing the I/O pins, so it's not anymore available. That's, I think, enough. We can, yeah. So what we showed here was that, OK, so in order to exploit the process, we get network access, we understand the process, and of course, we have to actually bypass the host space intrusion detection, right? So we bypass host space intrusion detection within the PLCs, and then we can manipulate the controller and do whatever we want. But it turns out that actually it's not, again, as easy as we think. We also have to exploit the OS and services within the PLC. In order to execute our attack, which I showed to you, we needed to have some kind of system-level access to the PLC. And we were assuming all of these protections. For example, you can't just manipulate the logic of the PLC. So when that comes to our mind that, hey, there must be some kind of buffer overflow, for example, exploitation in a PLC. And well, I think if you follow ICS cert reporting, in the last 2-3 years, there are actually few buffer overflow exploits for the PLC itself. So that's actually where our main story begins, embedded binary security. PLCs are embedded systems. So actually, I refer to embedded systems in general instead of just focusing on the PLCs itself. So actually, buffer overflow in general in industrial control systems are actually a big part of the problem itself. So like, as you can see, we have like 19% of the reported vulnerabilities as is reported by Kaspersky for ICS products are actually buffer overflow vulnerabilities. So that's one issue. And another problem is that embedded software development and, of course, PLCs are dominated by C programming language, which is, as we all know, is not a type-safe or safe language. So 66% of embedded software development is dominated by C. And exploitation, actually, of these embedded devices are not because it's so hard to exploit these systems, but because actually the first steps to get access to these devices, to understand them, is not available to us. It's like there are like certain constraints in these embedded systems which make the exploitation harder, not because the exploitation itself is hard. And once you actually find the exploitation and as we call it, weaponized exploit, then actually you have a long shelf of life for that exploit, because lots of these embedded devices generally take long time until they get updated. And so, for example, we are now in Germany and also in Netherlands. We are teaching exploitation in embedded systems. So, for example, ARM exploiting, how to write exploits in ARM, which is now lots of people talking about. But also, we are actually looking at engine control units, how somebody can actually do exploitation over the engine control units, because we believe that next step is that once we solve the problems of, for example, CAN bus, CAN FD, new protocols from Bosch, there will be exploitation over the ECU itself too. So we are actually working on how, or in this case, context-safe injection exploitation in tri-core CPU TC1797. And we are going to teach it from next semester in Germany. But to protect the embedded system from exploitation. Generally, like in general purpose computers, we actually learn it from general purpose computers. So we normally, when you have a buffer overflow, what we do is that, as an attacker, is that you just get a buffer overflow and then you get your shell. But later, in general purpose computer domain, we actually had some other kind of protection which made the exploitation much more complex. So we actually not anymore could just jump to our shell because there was some kind of protection, such as ASLR. So you needed info leak to find the addresses to jump in. And also, there were other things. So for example, write execute protection, which you also need other kind of evasion techniques. And also maybe the system have some kind of sandbox. So, so there are some protections there out there which we had to bypass. And so getting the system level access, as I showed to you, like to the PLC, which was prerequisite for an attack, which I demoed, it was not as easy as we thought. So we had to actually bypass those protection mechanisms. So for example, ASLR, data execution prevention, as they call it in Windows, or XN, and other kind of protection mechanisms exist. And here is actually how an exploit flow vs mitigation works. So generally, what you have is that you have your exploitation mechanism, which you want to overwrite the return address. And what will happen is with one specific exploit mitigation protection system, is that you have stack canaries, meaning that you cannot just overwrite the return address to whatever you want, because if you overwrite the canary, then you can never return, because you corrupted the canary value and the system checks before it actually do a return. And next was, for example, so this is a stack canary protection. So that's how it protects us, the embedded systems or general purpose computers. The next step was that normally what you do is that you want to jump to your shellcode. But ASLR, or address space layout randomization, what it does is that it randomizes the addresses within every time you run the application, meaning that you cannot just know anymore where to jump or where to execute. So that was another countermeasure. And then, of course, we had write execute protection, or XN, or DEP, and lots of different names, which attacker cannot anymore just write somewhere and then execute the value. Of course, this protection mechanism can be bypassed by return-oriented programming. And then you can get an exploit. So looking at embedded systems, so actually we did some research so in embedded operating systems. So it can be real-time operating systems and others. So actually this protection mechanism, as we might think, is not that much often seen in this embedded system. So actually for executable space protection, as we call, or XN, only 43% of embedded systems are actually supporting such protection mechanism. For ASLR, or address space layout randomization, it's even less. It's like 20%. And for stack canaries, for example, the value is only 31%. So most of them are actually, we can say that they don't even support these protection mechanisms. And if we, again, go further, look at most constrained embedded systems, so embedded systems which are running, for example, on an MCU, then it's actually worse, because executable space protection is, for example, 15%. You will have non-ASLR in this embedded OSs, and for stack canaries, you only have 5% support. So we are looking at, so far, looked at how many of them are actually supporting these products, right? How many of them are actually supporting this kind of exploit mitigation, sorry. But the question is, how actually those who are supporting it, like, implemented it, or how good they are, right? So that's another part. So that's where we're looking at real-time operating systems and real-time operating system security. So generally, in PLCs specifically, we have real-time operating system, because PLCs are actually hard real-time machines, mostly, not always. So you can have soft or firm real-time requirements, but mostly the PLCs are hard real-time machine. And this is super, super important for lots of vendors to maintain the real-timeness of their system. So therefore, they are running a real-time operating system. And of course, meaning a deadline in a PLC, in a process, in a physical process, in some cases at least, can cause like damages to the physical process. So it's unacceptable. Therefore, real-timeness is really, really important in the PLCs. And actually, surprisingly to us, there are actually very few public information about real-time operating systems. Long time, nobody actually looked at them. And while at the same time, they're actually being used for extremely, and I say extremely important applications. They are being used, and for everything you can think of. And there are few research on them. So, and of course, there are usually 4 constraint platforms, so the embedded devices which are resource constrained. So another thing is that there is a kind of I call polyculture, meaning that you have lots of different vendors in this market, which are producing different kind of operating system. Some of them you might heard, some of them not, but they are there. And actually, it could be full, this page, but just didn't decide to make it full. So here is an example. We were looking at a QNX real-time operating system and how, for example, they implemented their exploit mitigation and exploit like buffer overflow, for example, protection mechanism they have within their operating system. And QNX actually, to be honest, for lots of people are like secure, like BlackBerry, like phones for lots of presidents of countries, like they are using it because they say it's secure. So, and of course, it's a market leader in automotive too. So QNX is famous, at least in automotive industry. QNX generally is like a message-based operating system, meaning that you have actually a microkernel instead of kernel. So you don't have your device driver or file system in the kernel. It's just outside of the kernel. And you just communicate with the different services via message buses. So it's kind of like socket programming, I say. So here's an example of a message-based communication between a process with another process or with the microkernel. So what is happening here is that in a microkernel, what you have is that just listening to a specific gate, let's say, with a specific number, and then the processes are communicating with you, sending a request to communicate with this interface. And that's message-based communication. And surprisingly, they also support libc, meaning that you can actually write your code in C normally, and what will happen is that there is something called QCC linker, which actually compile your code. So it's, instead of GCC, you have QCC, which compile your code to QNX compatible binaries. So remember again, that's a point I want to emphasize here. So this is the story. This is the main story we are looking at. So we want to exploit the process, but we had to get network access, which we did some research. We had to understand better the process. We have to bypass host-based intrusion detection. But for doing that, we have to exploit the services. But what I understood is that there are some exploit mitigations there. And here is it. For example, ASLR. And we are looking specifically in QNX ASLR. So one of the things we saw was that in the interrupt service routine of QNX, from the user space, actually the interrupt service routine actually save the address which is jump to the kernel, to the microkernel, are being saved in the user space. And that is crazy because, well, first of all, by having that address, and it's always jumping to a specific routine in the microkernel, the attacker can actually calculate all the addresses, for example, in the kernel, because you are basically leaking an address by saving it to the user space memory. And even worse, actually, is that it is rewritable, meaning that attacker actually can change the address which you are jumping to the microkernel, which means that you can actually have an arbitrary code execution in the microkernel, because you can just jump anywhere you want, right? And that's not good. Next, if you think that's complicated, we can actually look at another one. They have actually a process monitoring kind of, so it's like PS in Linux, which you can actually look at the different processes. And actually, these processes are actually already leaking all of this information about base addresses, registers, and every info about the process. So you actually have ASLR implementation, but in the same time, you have a process which actually like leaking all of the addresses. So I think it's design flaw, which already fixed, I think, in a QNX 7 release last month, reported by the reports we provided them, and lots of other things. Another example is rel-row protection. So rel-row is a protection mechanism which protect different part of the binary from being overwritten. Okay, so you protect different sections of the binary, and one of the most important ones are global offset table. Here's an example which we have as the rel-row protection, as we can see, is protecting global offset table of a Linux binary. So it's a Linux binary, it's not QNX. So what we see here in the second line of those codes is that the value 004D ED8, and this is a starting address of rel-row protection, meaning that it doesn't let you overwrite anymore from this address to the point plus 0128. And this is the range which we can calculate. So 08 in the right up GNU rel-row 08049ED8 to 0804A000. And if we look at the global offset table, GOT, in the end, we can see that that address, 08049FDC, is actually within the range of GNU rel-row, meaning that the binary is protected. So this is how a proper implementation of rel-row looks like. And now let's look at QNX. So this is how QNX implemented the rel-row protection. So again, the address of rel-row protection starts by 08049F2C. And it continues plus D4. And the range will be, as we can see in the top right, GNU rel-row from 2C to 00. I didn't want to, so F2C to 000. But look at the GOT in the last line, not last line, one before last line. So what we have, global offset table address, is actually completely outside of the rel-row range, meaning that even when you ask the compiler to protect the binary with rel-row, the compiler actually doesn't generate the binary with full rel-row protection, meaning that global offset table, which is the most important part here, is actually not protected, even when the compiler says it is. So last is random number generators. So random number generators are actually underlying protection, or underlying security mechanism for lots of security mechanism. It's underlying system. If you have ASLR, ASLR needs randomness, a source of randomness. And random number generators within the operating systems or real-time operating system actually provide this source of randomness. Also, stack canaries, there are some kind of random data there. So there's also there, which the random number generators are important. SSL, SSH, all of these things rely on these random numbers. And that's why it's important. So just before I start, just very basic concept. So randomness, I know lots of people might disagree, but I just say everything, which is predictability of guessing them is like less than 50%. And then there is something called entropy. Entropy means that, so it's kind of a measurement of how much information are unpredictable. Okay, so that's entropy. So if you have a high entropy, meaning that you have very, very unpredictable kind of data there. And random number generators generally can be true sources of randomness, or can be pseudo. here's an example of how QNX implemented randomness or random number generator. They provide a random number generator as its operating system service in dev/urandom. And they have two sources of entropy for generating a random number. And one of them is actually a boot time entropy source, and then runtime entropy sources, which we explained. And then they pass it to a function called yarrow. It's very, very famous, actually. So then they generate random number. And here's an example of, not an example, actually, how QNX generate the random number at boot time. So they are using actually system time, clock cycle, process PIDs, and device names. And obviously, some of them are actually not at all random anyway, or not a good quality of entropy. But anyway, so they make it a SHA-1, and then they pass it to yarrow function, which generates initial states of the random sources. And we actually instrumented some functions within random number generator of the QNX, and did an entropy analysis over how random is the data there. And as you can see, that those dark sides are actually the places which the data are not random, or doesn't have a good entropy there. So actually, average entropy of in the QNX boot time entropy was actually 0.02, which is far less than 1. It's not good. And then there is a runtime entropy. So at the runtime, you also have some kind of random sources. And here, for example, it uses clock cycle or interrupts and system info and some kind of undocumented sources. Crazily, actually QNX before version 6.6 actually didn't have any kind of receipt control, meaning that the only source of randomness was the boot time entropy. So the QNX actually didn't use at all, even while they implemented it, but they didn't use and they didn't have any kind of receipt control. Therefore, they didn't use any kind of a runtime entropy which they were generating. And well, later in QNX 6.6, which before 1 month ago was the latest version of QNX, was actually later they added the receipt control of the QNX. But the problem was that they were not actually looking at the quality of the entropy of the data which they were getting. So that was an issue. And we actually report all of these issues to the QNX, and partially they are fixed in QNX 7. Some of the algorithms which we suggested are actually being implemented in QNX 7 now. We are actually in close cooperation with the BlackBerry for their operating system. Now we are looking at the microkernel. Next operating system is actually a aviation-based real-time operating system. It's a DO178B real-time operating system. We reported this problem to the vendor around 9 months ago. They told us they don't have any plan to fix it, and they asked us to not mention their name. And we are not going to mention their name. So this operating system actually provides random numbers or pseudo secure random number generator, but as a service again, so in dev/urandom, but they are actually using just a random function in BSD. And that's crazy, because if you look at the description of the random function, it says that it's not cryptographically secure. So you shouldn't actually use it for cryptographic elements. Yet still, the operating system provided as a secure random number generator source. And here's the example. So this is a local reseed attack, meaning that we can actually feed our initial entropy seeds to the operating system, because the operating system doesn't check that. So here I'm writing value 0x1337 and to the dev/urandom, because actually dev/urandom in that operating system is system-wide writable. Anybody can write to it, and that's not good. So here I wrote value 52 to the 1F5F. Just remember that. So this is the value which we are reading 32 bytes twice, and we see twice the same value, because it's actually a value which we feed as an attacker. And then let's generate a SSH key. Okay, so we generate a SSH key, But as you can see again, you see the value 52 to the 1F, 5F. This is the value which we are setting, like to the SSH key generation. What will happen is that, well, we can actually brute force this private SSH key of the device because, well, we had actually had the initial control over the seat, which was being passed to the OS services. So yeah, so that's another one. Last one is VxWorks. Actually, VxWorks is famous in lots of industrial equipment also are using it. Looking at the random number generators, actually the operating system does not at all provide any kind of source of randomness. So actually the operating system doesn't provide their view random as a secure random number, a pseudo-secure random number generator. And therefore, as you can see in different kind of libraries, they are actually either using time or date, or sometimes none, and asking you to provide some kind of randomness, meaning that the developers have to do that. And developers, not all of them are actually having the same quality, meaning that some of them are actually looking around in forums and asking if they can just use get time of day function, or for example, ran function as a source of secure randomness, which is not good. And if you think VxWorks doesn't provide this, they are very bad. Actually, they are not alone. Actually, if we look at only 40% of the real-time operating system or embedded OSs are actually supporting secure random number generation, regardless of their quality. We talked about the quality of them, but regardless of their quality, they are actually, majority of them actually do not support at all. So we said lots of problems, but what are the solutions? How we can make it harder for attacker to gain their point, which in that circle which I was showing, getting access to the process and exploit the process. So one of the things we are suggesting is control flow integrity. Control flow integrity meaning that you can generate a control flow graph of the application. So let's say you have a PLC runtime. This PLC application follows certain paths. So it calls a function, a specific function. Let's say a function A calls function B calls function C, or function D. And then function D calls function E. So what we do is that we are modeling this path, what we call control flow graph. And then what we do is that we are saying that, OK, this is the path which a right application have to take. So as you can see in the next step, if function A call B, and then B call D, and then D call E, this is a valid path. And again, so if A to B, B to C, C to D, and then D to E, again, is a valid path. But A to B and then B to E is not a valid path. This is control flow integrity. So what we do is that we are looking at the binary of the applications, look at how which flows of information or execution paths it's taking. And if it's not in the path which we expected, we can kill the software. But it doesn't work because, for example, this is a very well-known concept in general purpose computers, but not that much oftenly seen in embedded systems. And there are reasons for that. So first of all, the embedded system, lots of them are actually based on low worst case, it's based on worst case scenarios. So as we said, for example, a PLC is a hard real-time machine. So you can't just provide me an average performance and tell me, yeah, it's like 5% overhead on average. I don't care about average. I care about worst case scenario. And that's make it hard. And they are, as I said, any solution must be real-time friendly. And also, we cannot just, like any other control flow integrity mechanism exists, we can just kill the application. We have to actually maintain the availability of the system. For example, you can't just kill a PLC in a I don't know, a power plant just because you found a control flow attack. And another problem is that we have some kind of commercial off-the-shelf binaries, and which we have to also take care of that. And of course, we have to have a solution which doesn't hardly rely on hardware features, so performance measurement units or LBR. So actually, we've worked on some kind of protections, actually. 2 protection mechanisms. UShield is actually open source right now. It's generally for all embedded systems. It also supports commercial off-the-shelf binaries. for embedded systems and contains some heuristics. And second is ECFI. That's not yet open source. It's a hard, real-time, friendly control flow integrity. It's already tested in PLCs. We also asked two PLC vendors to cooperate with us, which they didn't. So we actually did it by ourselves in a PLC. And there will be some papers about it later. And we're also actually looking at more real-time operating systems. Some of them have EAL6+ from NSA. We're also looking at the security, how they actually got that level of certification, how secure they are. And so here is again, this is a picture of my work. And so we try to understand better the process. So what are the problems, and inform the utilities about the process problems they have. Now the attacker, because we introduce control flow integrity, the attacker have to bypass control flow integrity in order to exploit the services. And then the attacker have to bypass the PLC host-based intrusion detection, which we actually introduce one technique. But in the same time, we also introduce a defense for it. So for pin control attack, which we discussed actually this year in S4, we already have a protection mechanism as well. And yeah, I think we have to keep raise the awareness. In short term, we have to address those, bring those mitigations which we have in general purpose computers to embedded world. And long term, I think we need to have some kind of type-safe language adaptation in the embedded world, and also secure embedded patching and updating. This last year, I think FTA also introduced some kind of prize for providing such solution. And of course, IoT standardization, and that's it. If there is any question, I'm happy to answer.
Thank you, Ali. Do we have some questions for Ali? So this is kind of a basic question, but maybe I was a little confused here. In your pin configuration, and also when you get into, when you're doing some of the exploiting of the ASLR and other things, you talk about requiring access to do that. Is this just access to a network?
No.
Are these devices listening on ports that you need so you can get into this level of configuration information, or is that where you have to find some exploit then to dig down deeper? Can you explain that a little more?
No, so the access means that we have to actually have system level access. So for example, a telnet access to the device or a buffer overflow exploitation. So lots of this, for example, in the case of PLCs, I also talked about it in S4 2013, some of these PLCs actually had, on that time, backdoor passwords, right? We assumed that that is solved. But the next step was that we were assuming that for doing this exploitation, we need some kind of terminal access or system level access, so not in the network, but actually inside the PLC. And for achieving that, lots of attackers, what they can do is that having a buffer overflow, meaning that it can immediately give you system level access because you can execute your shellcode. And that was the point. So yeah, no network, but actual exploitation. And that's all of our countermeasures which we designed, was to avoid also that. Control flow integrity is also to protect before it happens, before the attacker gets access. We avoid it. We alert the operator about the issue.
Okay. Other questions? Okay.
I'm Martin Rannefeld from QNX Consultants, and I'm consultant in the security field. I'm not a hardware guy, so one question. How do the PLC react if you don't have any documentation what the pins are doing? So you have to find out how the configuration is. Is there a chance for me as a defense to see it in my appliance or somewhere that you have access and you're probing the pins?
Yeah, that's very good question, but it's hard to answer because it really depends on what kind of protections you deployed within the host of your system, which most of the PLCs don't, for example, in the case of PLCs or other embedded systems. But beside that, yes, it is possible that you know that, but it takes time. And we already designed something called Ghostbuster, which actually trying to address the issue which the talk we had in Black Hat last year on ghosting the PLC. So we tried to actually look at the behavior of the, for example, I/O interface of the embedded systems or PLC, or how frequently the configuration of the pins are changing in order to raise an alert. So it really depends on your device. So if you have tools, like basic tools which we need to deploying like those protection systems, then yes. But if you don't, because lots of these embedded systems, they remove everything. So everything you don't need, you just remove it. And that's kind of issue too, because if you don't have basics, then we cannot actually provide the protection, for example, based on the things which we design or things which you might design by yourself. So it's really, really subjective to your device.
Thanks.
I think we have time for one more. You mentioned ghosts. That makes me, ghosting your presentation at Black Hat. When you're talking about these things, if you have access to the supply chain and you can open up, you can unbox these things,
and then
can you hide some nasty things in these real-time operating systems that might be of value to an attacker in the later stages?
Yes, a lot actually, and that's actually what we do also to understand it too. So we are, for example, in different kind of devices. Sometimes we actually just buy to get access to it, and then we just return it actually. So yeah, I think it's a smart move that lots of people can do. Like you can just actually study the device. You just need, for example, in the case of pin control attack, you just need to know the processor type, and that's all you need, and then you are done. You don't need anything anymore from the vendor itself. So because the firmwares are always out there, some of them are obfuscating it, but we find always some ways to actually bypass those obfuscations, and then yeah, and then also if you know the hardware types, then you are done. I think you don't need the device anymore after, except for validation. That's it.